Hello everyone. In the last video, we started the basic concept of genetic algorithm. Uh, in this video, we will try to apply the concept of genetic algorithm, its various operators and fitness function to solve the job shop problem. So first of all, we need to understand what is a job shop problem and how can we represent it in such a way that it can be solvable with the help of genetic algorithm. So first of all, we have three manufacturing units in a shop represented as M1, M2 and M3. Each of these units perform a different job, a particular job to manufacture a different product. So now we need to represent the working state of these manufacturing units, and simply we can have a boolean variable where one represents that the unit is in on state, that is manufacturing a product, while 0 represents that the unit is in off state, means that it is currently not manufacturing a particular product. So these variables 0 and 1 represents a particular state of the manufacturing unit at an instance of time. So uh, in mathematical term, we can represent that 101, where we can say that m1 is in on state, m2 is in off state, and m3 is in on state. So as a whole, it will be called as a chromosome. So now the objective is to find an optimal solution or optimal chromosome, such a chromosome which yields to the maximum profit. Of course, it is a simple problem, and we all know that the maximum profit will be yielded when all the manufacturing units are in the on state, represented by 111. So we all know this is a simple problem, but this is just for the sake of understanding the concept of genetic algorithm operators. So now we have to proceed and try to apply the concept of genetic algorithm to see how can we reach to the state 111 from a given set of chromosomes. So first of all, the first step which we need to follow is to represent our solution, and over here we have chosen it in the form of a binary variable, that is 1 for on, 0 for off. So the chromosome which we are seeing over the screen represented by 101 means that M1 and M3 are manufacturing or working, while M2 is not manufacturing. Then second thing which we need is a fitness function. It is to be considered critically that fitness function uh, generally is different for different problems. So over here we represented our fitness function by just concatenating these three values of the uh, working states of the manufacturing units, and then converting them into their decimal equivalent. So decimal equivalent of 101 is 5. So the fitness value of this solution or this chromosome 101 is 5. So now we have to select a population of the solutions. Of course, in general we have a number of solutions when we apply genetic algorithm in the real world environment, and we have numerous solutions, and we have to select a population to be worked upon and consequently calculate their fitness value. So suppose we have selected 4 solutions. You can see on your screens that first solution is 001, means that M1 is working, M1 is not working, M2 is not working, and M3 is working. So only one manufacturing unit is working. So it can be represented by fitness value equal to 1. Similarly, the second solution is M2 is working while M1 and M3 are not working. So binary decimal equivalent is 2. Similarly, for the third solution, fitness value is 6, and for the fourth solution, fitness value is 5. So now in the last video we have discussed in genetic algorithm we have three operators. First one is reproduction, second is crossover, third one is mutation. So with the help of this example we will try to understand the application of all the three operators. So let's start with the reproduction operation. So reproduction means generating a number of solution sets whose fitness is large enough to compete in an environment or search space. So suppose in the last slide over here we have seen we selected four solutions or four chromosomes. Now we need to reproduce them. So suppose we generate randomly 500 sets of such solutions. So in one set we have four solutions. So if we have 500 sets, then obviously we will be having 2000 chromosomes. So among these 2000 chromosomes, it is obvious whatever the distribution we are applying, it is obvious that we will try to have those chromosomes in the large quantity whose fitness values are large. So in the previous table, if you can see, the chromosome 110 has the highest or largest fitness value, then chromosome 101 has the fitness value lesser than the 110. Similarly, you can proceed. So what I'm trying to say is that the chromosome with the highest fitness value has the largest or highest probability to be appearing in the resulting 2000 chromosomes. So for the sake of explanation or understanding, I have generated a number of chromosomes. You can see over here uh, that if you try to see this, then what I'm trying to specify over here is that the appearance of 110 is highest. So among the population of 2000 chromosomes, the probability of the chromosome having the largest fitness value is the maximum. So now after the generation of 2000 chromosomes, now we have to randomly choose the number of chromosomes for further competition. So now we have to then apply the crossover operation, which is the second operator in genetic algorithm. So as we discussed in the last slide, that the probability of appearance of the chromosome having the highest fitness value is maximum. So when we randomly select a number of chromosomes, then it is obvious that the chromosome whose appearance is highest is to be selected more frequently or most number of times. So for the application of crossover, suppose I have to select two chromosomes, two pairs of chromosomes. So in pair A, we have a chromosome 110 and 010. In pair B, we have a chromosome 101 and 110. So in these two pairs, you can see 110 is a common chromosome. So it is simply due to because the appearance of 110 is highest due to its highest fitness value. Now to apply the crossover operator, we need to randomly choose a crossing site. Crossing site is nothing but a bit position which I have to interchange with the selected among the selected chromosomes. So we have two pairs A and B. So for pair A, suppose I have selected first bit for interchanging, and for pair B I have selected 0th bit. So in the figures on the right side you can see the above figure representing the crossover of the first pair, pair A, and in pair A we have to interchange the first bit. So when we change the first bit among the two selected chromosomes, the resultant will be 110 and 010, which is absolutely the same as the parents or the previous chromosomes. So in this case we can say there is no benefit of having the crossover. Now in the next pair, pair B, you can say we have selected 0th bit, and while interchanging the 0th bit we can have two resulting chromosomes which are 110 and 111. So now if we in total we have four new chromosomes, you can say 110, 010, 100 and 111. So now we have to check their fitness values. So the fitness value of 110 is 6, 010 is 2, 100 is 4, 111 is 7. So over here we have reached to a chromosome whose fitness value is larger than any chromosome in the previous existing set of chromosomes or previous existing solutions. So we have generated a better solution or optimum. At this time we cannot say exactly whether it is optimum or not, but yes, we can say that it is a better solution than the previously existing solutions. Of course we as a human know that it is the optimal solution, because we cannot have a larger value than 111 of having a boolean variable in the form of 3 bits. So now this is the fitness values of the newly generated solutions, and we have a new solution, new chromosome having the better fitness value. So we can say that our crossover operation is successful at this time. So now quickly we will coming to the application of mutation. Generally you need to keep in mind that the frequency of application of mutation operation is way smaller than the application of crossover. Or we can say, if we talk about the exact number, then we can say once in 100 times, sorry, 1000 times. So we generally apply mutation once in 1000 times. So this is generally frequency of mutation. Generally we try to apply crossover much more than the mutation. So but for the sake of explanation, I am just considering a chromosome 010 to be mutated. So now if we all know that in the last video we have discussed that in mutation we need to flip a particular position. So we only have two possibilities for a particular bit, either 0 or either 1. So when we have 0, we can flip it to 1, and if we have 1, then we can flip it to 0. So the resulting chromosomes from 010 can be 011, 000 and 110. Now if we check the fitness values of these chromosomes, then it will be 3, 0 and 6. So if we come back, if we go back to the first set of solutions, first population of solutions, then we can say that after the application of mutation we haven't reached any better solution. So we can say for this set of chromosome which we selected as 010, we cannot generate a better solution. So it is resulting in the almost same fitness value. So this is all about the job shop problem, and in conclusion we can say that by the application of crossover we have reached an optimal solution for the job. Uh, the content of this video has been taken from the book of Artificial Intelligence authored by Ellen Rich, Kevin Knight, and Shiv Shankar B. Nair. It was the third edition of this book series, and it was published by McGraw-Hill Education Private Limited. Okay, so I hope you have got the concept of the genetic algorithm operators, and still if you have any confusion or doubts, please write me in the comment section. Thank you.